we've gone through, finished up Chapter 2 and Chapter 3. So Chapter 2 was about, all the different methods for calculating a surface green function. And there were two different types. One was the iterative methods, in which there was a dumb iterative method and the decimation method. So one had roughly linear convergence, the other had exponential convergence. And then there were the exact solutions, these mode space solutions, which required this generalized eigenvalue solution. And then we went on to, cover all of Chapter 3, in which we showed how the general form of the equations don't change at all when you go to finite cross-sections. But you just have to define the blocks properly and order your Hamiltonian so it's in this block tridiagonal form. And if you order your Hamiltonian so it's in this form, then every equation we've written down just continues to hold. It's just that the blocks are a lot bigger. And so that, I guess, brings us up to where we are now, which is the Chapter 4 and the recursive green function algorithm. So this is where we are now. And this is sort of really where the fun begins. Because this is really the core soul of all of our non-equilibrium green function programs that use this to solve something. And this is, as in Chapter 1 when we found the form for the transmission coefficient, and you needed to get, it was like, gamma 1,1, G1n, gamma nn, Gn1 dagger. And you needed to get the far off diagonal elements of the green function. And then we got a more efficient one, which only needed the corner block. And we said later we'll figure out how to do that, how to just get the corner block of an inverse. Well, this is the way you do it, using this recursive green function algorithm. So we will go through this carefully because this is what you really need to understand and be able to use. So first we'll talk about Dysons equation, which is where it comes from. And Dysons equations, you have a Hamiltonian, which is some what you call unperturbed part, H0, plus something added on, which we're going to treat using Dysons equation. We're going to treat it exactly now. So the recursive green function algorithm treats this term exactly. But in general, if this could represent like your electron-phonon interaction term, in which then it would become something perturbative. But for now, the way we're going to be using Dysons equation is just an efficient way to solve this to get what we need and nothing more. So we'll define the green function of H0 in the usual way. We would solve E minus H0 G is equal to I. So the little g will be used for H0. Or the usual, G is E minus H0 inverse, or another thing, usually you don't think of it like this, but G inverse is E minus H0. So G inverse is a very efficient way of writing E minus H0. So that's all good. Of course, we want the green function of the full H. And so the green function of the full H, I'll use uppercase G. So you want the green function of the full Hamiltonian, which is also defined in the usual way. E minus H acting on G, the big G, is the identity. or G is E minus H inverse. And then Dyson's equation for G, I'll just write it down and we'll show that it's true, is G is equal to little g plus G V big G. And this you can think of as matrix multiplication in our localized orbital basis. And so it's pretty easy to prove if, let me copy and paste it. So all we do is multiply both sides of the equation by little g inverse. So I have little g inverse acting on G is equal to the identity plus VG, right? And then I move the VG term over to the left side. So I have G inverse minus V acting on G is the identity. Well, little g inverse is just E minus H0. That's E minus H0 minus V acting on G. It's the identity. And H0 plus V is just H, so E minus H acting on G is the identity. So this is indeed the exact solution for your full green function. Because this implies this, and this is the definition of your exact green function. Another thing we can do with this equation here, and the way that you would expand it out in a perturbation series, for example, is to just start iterating it into a power series. So G. So I'm just going to iterate that equation at the top as a power series. It's equal to little g plus G V little g, and then plus GV GVG plus dot 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 plus, I guess it'll be, GV to the n, or how do I want to do it? Oh, little g, I'll do it this way. Little g times VG to the n plus dot 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 dot, right? That would be what it looks like if we just start iterating that equation as a power series, sort of back substituting. Have you ever done this? Usually you do this in a computer science class or something, right, for iterative algorithms. So you take, so the first iteration is the zeroth, where you just, for this big G, you put in this. And then you keep doing this over and over again to generate the full power series. Never done anything like that in like a control theory class or something? Computer science class? Or even your quantum mechanics class?
I mean, you haven't done it numerically, but this calculation you have done.
Just sort of this.
Analytic.
Yeah, analytic. Just I don't mean numerically. I mean just taking the equation and then iterating it out as back substituting it to generate this infinite series.
Well, we've done that in quantum mechanics.
What's that?
No, we've done that in quantum mechanics, giving the time-dependent product.
Yeah, right. That's where you do it.
The potential here is also time and position dependent, right?
We're just treating, for us, it's just going to be, there's no time dependence. And for us, it's just going to be a matrix element. This V will become some T's. If I have a power series, right, I can sum a power series, so that's equal to little g times I minus VG inverse. right? That's the sum of the power series of 1 plus x squared plus x cubed, dot, 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 where x is now Vg.
For small perturbation, right?
Yeah, it's only valid for x less than 1, but let's just assume we can go ahead and sum it. And, well, multiplying in that g, that's equal to g inverse minus v, quantity inverse, which is our E minus H0 minus V inverse, which is our, by definition, our G. E minus H inverse, that's G, right? Right, all I used was a sum. What is it? The sum n equal to 0 to infinity, x to the n is equal to 1 over 1 minus x. Is that right? For x less than 1. This is a class. I mean, this is the basic power, and this is the one thing in term, probably the one infinite sum you should know immediately. This is probably the most important one. Okay, so that's just another way of looking at it. And then if you wanted to, if it really were a small perturbation, then, you might just keep the first term, for example, that g equals little g plus gvg, right? That would be like a first order treatment of your perturbation. But we're going to be using this. This is sort of the foundation for what we're going to be doing, and we're going to be treating it to all orders exactly. Any questions? Are we all good with this? Want me to actually expand out that, create that power series? Starting from that first equation? Adiva, could you do that? Probably yes. All right. I just do, yeah. There just seems to be some stunned looks on people's faces. I don't know. I mean, if I do my first back substitution, I have G plus GVG, right? That would be my first sort of approximation for big G. And then I substitute this in again. So then if I substitute this in for the big G, then I get, G. The first G always goes along, G plus GV, and then GVG, and then this, what do I got? Now, how do I got to keep my first term. What's that?
That was a big G. First, you have to submit G for G plus GB, big G. Then it will work.
Okay, see, you do know how to do it. Okay, excellent. Okay. Let me see. So if I got G, that would be my first, and then I got to, oh yeah, GV. Oh, right. Okay. This term, right? This goes back there, so I would have my GVG term plus my GVG term, and then you do it again and again and again. You generate your infinite series. Okay. That's all good. So this is all about Dysons equation. So you break up the Hamiltonian into these two parts. You define what this is also referred to as the Baire-Green function, especially when it's some many-body perturbation. So the Baire-Green function is just the green function of the unperturbed Hamiltonian. And then, well, this one down here would be called your dressed green function, but we're not really doing many-body perturbation theory. So this is just, for us, this is your full green function. Okay. And we showed that this was indeed an exact solution for the full green function. Okay. And showed how it can create this power series expansion, which you could truncate if you wanted to make an approximation. Okay, that's all good. Now there's also what people refer to as the alternate form of Dyson's equation. And the alternate form looks like the full G is equal to the little g plus the full G V times the little g. And this is also an exact solution. All right, so on the last term, I just switched the order of the big G and the little g from before. Again, if we the way we do that, prove this is we multiply through by G inverse from the left. Okay, and so if we do that, we have big G times G little g inverse is equal to the identity plus big G times V. And well, I'll move the V over to the left hand, the VG term over to the left hand side again. And I have big G times G inverse minus V is the identity. And then I have just multiplying through by the inverse of this term, I have G is equal to, G inverse is E minus H0, so that's E minus H0 minus V inverse, which is indeed the definition of my full green function. And these two forms of the Dysons equation make use of the fact that inverses commute. So G inverse is G inverse G. So writing that out, we have G times E minus H is equal to E minus H G, which is the identity. Inverses commute. Doesn't matter which side you write, put the order of the matrix multiplication. Okay, so those are the two forms of Dyson's equation that we're going to need to develop our recursive green function algorithm. And so first we're just going to do an example to start getting used to this and how we actually use it. So what we're going to do is go back to our infinite chain problem. And we're going to have an ideal lead over here on the left. And this will be site 0, minus 1, minus 2, etc. Site number 1. So site 0 and site 1 are coupled by the matrix elements T01 and T10. And I'm going to break the coupling. I'm going to assume basically a hard wall boundary condition here. So there's no coupling between site 1 and site 2 or anything else. So my system ends at site 1. It goes back to negative infinity back here. And so the setup of the problem is that I know the surface green function at site 0, and I want to use this Dyson's equation to calculate the exact green function at site 1. So you know the exact it is a surface green function. We're going to use Dyson's equation to calculate G11. The matrix elements of V are pretty simple. They're just our T10 and T01. Those are the matrix elements of V. And I'm going to write out our Dyson equation and write out the indices. So writing out the indices of the matrix multiplication, I have Gij is equal to little g I plus sum over KL of G I K, V, K, L, big G, LJ. It's writing out what that matrix multiplication means in terms of the indices. Okay, but V only has two non-zero matrix elements, so that sum collapses, and we have that G 1, 1 is equal to little g 1, 1 plus little g 1, 1 T10 big G 0, 1 plus little g 1, 0 T 0, 1 big G 1, 1. And since this isn't connected to anything to the right, I'm also calling this a surface green function. Right, so all these guys, everything's a surface green function here. There's nothing beyond site 1 in this problem. So the uppercase G's include the coupling T. I mean, they are our exact green functions, including the effect of the T10, T01, and everything through and including site 1. And the lowercase g's are calculated setting the T10 and the T01 to 0. So the lowercase g's, I mean, they're just for this system that ends at site 0, right? 0 minus 1. So they're calculated for that system that terminates at site 0, where we've set the coupling to the right equal to 0. Dot, 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 back to negative infinity. So if that's the case, then I guess this isn't. There's this lowercase g, this guy here. So I guess it includes this site, but with no coupling, because little g11 is just this site sitting all alone there. Right? Little g11 is e minus epsilon 1 inverse. So this is a site not connected to anything at all, just sitting there isolated, because what we've set to 0 are the T10 and T01. So this is a system for the little g's. A semi-infinite lead up to 0 and one isolated site sitting all alone. Site 1. Now if this is the case, if this is a system, then what can we say about this term? Well, again, this is a green function. What's the physical?
Impulse response.
It's the impulse response of what?
I at 0 and the response at 1.
Mm-hmm. And what will that be?
I mean the right moving.
What will that response be? We're talking about this system right here. What will that response be?
e to the power minus I k.
Is site 1 connected in any way to site 0? How will there be any response at site 1?
Oh, sorry, if you T0, okay,
Yeah,
0.
that's the system we're talking about, right? T10 and T01 are 0. Again, this is a bear. And we'll formalize our notation better, but the hardest thing to keep track of when you first start playing with Dyson, these Dysons Equation and RGF, is keeping track of what's meant by the bare green function, what's included and what's not included. And so this is perfect example. So because there is, we set those for the little g's, we set the T10 and T01 to 0. Any little g that crosses that boundary has got to be 0. With indices that cross that boundary between 0 and 1, all those little g's have to be 0. And so what we're left with is that G11 is this little g11 plus little g11, T10, big G. Now the big G can cross that boundary because for the big G we include the T10 and T01. Oh, yeah, question?
Yeah, I'm sorry, if you're setting like T100, then shouldn't be the second term also be 0?
Why?
I mean, are we setting here T10 equals to 0?
You're only doing that when you calculate the little g's. But Dyson's equation, right? This is, the t's are our v's. We're now including them to calculate the full g. So in Dyson's equation, the v is not included in your little g's. The little g's are just the green functions of h0 alone, right? And h0 does not include v. And then we put it back, we put the v back in using this Dyson's equation to calculate the full g, which does include it. Okay, so we've got it down to this equation here, but now we've got a problem because we don't know what G01 is. Right? We don't know what this full G01 is any more than we know what the full G11 is. So what do? Well, we write another Dyson equation and hope that sooner or later we'll be able to close the set of equations. So we'll write an equation for G01. So G01 is equal to little g. I'll write out everything and then we'll cancel all the 0 terms. Little g01 plus g00 T01 big G11. And you just write this out following the indices, the order of indices that you have when you do matrix multiplication. So I'm going to write all the terms that would appear just from matrix multiplication and then cancel out whatever's 0. Plus G01 T10 G01. Right, so in every case, in every term I've written, the first index is 0, the last index is 1, and all the intermediate indices follow one after another. So it's the power of keeping track of your indices and writing stuff in order. And this is the way it will occur in the matrix multiplication. If you look up here, I to K, K to K, K to L, L to L, and L to J, up on our top equation up here. Okay, but again, we've got some bare green functions that are crossing the boundary, right? So any bare green function that crosses that boundary is 0. And so we're left with just one term, and that one term is only a function of the big G11, which is exactly what we need to close that equation right above it. So now I just take this term and I substitute it in for here, and we have a closed set of equations for big G11. So I have that G11 is equal to little g11 plus g11 T10, the bare G00, T01, big G11. especially after the discussion of the homework, you recognize this as the boundary self-energy due to the left lead. This is R due to the output of L. That's exactly the form of the boundary self-energy due to the left lead. And if we multiply through by G11 inverse, then I'm going to get G11 inverse acting on big G11 is equal to the identity plus this term, right? And G11 inverse is just E minus epsilon 1. And so moving that sigma term to the left-hand side, I get E minus epsilon 1. I'll write out the sigma term, minus T 1, 0, G 0, 0, T 0, 1, acting on G 1, 1 is the identity. And this is exactly the form that we derived for a surface green function. This was a starting point for our dim algorithm, because that big G11 in this case is the same as that little G00 by adding one node to a semi-infinite lead, providing all the T's are identical. Right? If this T10 and T01 are different from all the other T's, then they're not the same. Otherwise, this was how we got our dim algorithm for getting the surface green function. This was our sigma left. Right, so this is exactly our self-energy due to connecting to a semi-infinite left lead, and that's exactly what we were talking about in the discussion on Friday, where those T's then are, I forget what we called them, they're like the coupling to the resonant level to the lead. I forget what the notation was in that problem. We may have just called them T left and T right. Okay, so you've already seen that you have to carefully keep track of, some of the bare G's are connected to the left, to everything to the left, like all the way to negative infinity, like G00. Some of the bare G's are not connected to anything at all, like G11, which is just a green function of that isolated site. And in general, we're going to have green functions that are connected everything to the right, all the way to plus infinity. And so we need some notation to keep track of that, just to keep your sanity when you're manipulating these stuff, to know what's connected to what when you're doing your writing this stuff out. So the notation we're going to use and terminology, I'll keep it in red since this is so important. We have our left connected green function. We denote that with this leftward moving triangle. And it's connected to everything to the left. So it will be a surface green function at the end of some semi-infinite left region. So it's a surface green function connected to everything to the left of it. And, well, then we need a right connected green function with a little upward rightward directed triangle. And so this will be a surface, it's also a surface green function. And then there'll just be a G, a bare G, which I guess simplest sort of thing is just not connected to anything at all. Just like our bare G here, which was just E minus epsilon inverse. And finally, we reserve uppercase G for the exact green function that takes into account everything. So G is the exact G, including everything. Okay, so in terms of this notation, the way it's going to show up is we would say that since the G11 that we calculated is, since it's not connected to anything to the right, it's really a surface green function, we would say that G left connected 1, 1 is equal to the bare G11 that's not connected to anything at all, plus again the bare G11, T10, the left connected G00, T01, and again the left connected 1, 1. So that's the equation we just wrote down using uppercase G before. And now in this notation, it looks like this. And this keeps clear of what's connected to what. And it'll become more important when we have stuff connected to both the left and the right. Or final form, we had E minus epsilon 1 minus T10 G left connected 0, 0, T 01. Or just not inverse, just acting on G left connected 1, 1 is the identity. So yeah, this notation is necessary to keep track of what's connected to the left, what's connected to the right, and what's not connected to anything at all. Okay, now let's do one more example where we will calculate the form of the green function of our device using what we just did. So example 2. And so our device will be will consist of nodes 1 through n. Okay, again, a linear chain model, tight binding chain model, nodes 1 through n of the device. And you have the usual left lead and right lead. So that'll be minus infinity to 0, and the right lead from n plus 1 to infinity. And now the matrix elements of V, you're going to have 4 non-zero matrix elements of V. You're going to be your T10, T01 again, T10, T01, Tn, n plus 1, and T n plus 1 comma n. Okay, so we're going to write the Dysons equation for the green function of the device, for the exact green function of the device. So I have that G ij, or I and j are any two nodes between 1 and n, is equal to the bare Gij. So that would be not connected to the leads, only taking into account nodes 1 through n, plus Gi1, T10, G0j, plus Gi0, T01, G1j, plus Gi, comma, n, Tn, n plus 1, Gn plus 1, comma j, plus Gi, n plus 1, T, n plus 1, comma n, Gn, comma J. So those, we have 4 non-zero matrix elements of V, so we get 4 terms, not including just the bare G alone. 4 terms including the matrix elements, corresponding to the 4 non-zero matrix elements. Okay, which terms are 0? Which terms can I get rid of? So I and J are in the device. Device consists of nodes 1 through N.
GI0.
Yep, GI0 is gone. IN plus 1, very good. Right, everyone see that? Because they cross the device lead boundary, and those, for calculation of the little g, the bare g, those matrix elements that cross the boundary are 0, so there is no response across the boundary. Okay, so we got rid of 2 terms. That's good. And so now we have G ij equal to the little g ij plus the 2 remaining terms, gi1, t10, g0j plus gin, tn, n plus 1, gn plus 1 comma j. And now we're in the same situation we had before, where we have these full green functions across the device lead boundary. So for each of them, we have to write a second Dyson equation to close this set of equations. So I need to write a Dyson equation for this guy and for this guy to close the set of equations. So G0J is going to equal the, I'll write out all the terms, then we can cancel them. The bare G0J plus G00T01 big G 1 comma J plus G01 T10 big G 0J plus the bare G0N Tn comma n plus 1 the full G n plus 1J plus, how many more terms? Plus 1 more term, plus G 0 n plus 1 T n plus 1 comma n big G n comma J. And these are all the terms that would show up in your Dyson equation. And now which ones are 0?
G01.
G01 is 0.
0n. G, small G0n.
Yep.
0n plus 1.
Yep. And 0J. So that 0n plus 1 is like doubly 0, man. That crosses 2 boundaries. That's really a no-no. Right? But if you just, multiply out all your indices, starting from the 4 non-zero terms and where's our original? This, our original form of Dyson's equation here, and just multiply out all the non-zero terms. This is what you get. Most of the terms are 0. So actually every term but 1. So the only thing we have left is this. And so we plug that in for G0J. And we do the same thing for the Gn plus 1J. And I won't drag you through all that. We do the same thing for the Gn plus 1J. And so finally we get the G I comma j is equal to the little g I comma j plus g I comma 1 t 1 comma 0, and this is the term we just did. So this term here, I guess I have not been using my new notation, have I? No, the new notation, I mean, this is correct because there is no left connected or right connected bare G's. This is correct because if you look at these terms, right, this term is only connected within the device. Same here because I is within the device, and so it's bounded in the device region. It's not connected to the left or the right. Same with this guy, of course, because both I and j are in the device, and all the other terms are 0. Here it comes into play. So if I'm using my new notation, this guy should really be the left connected, right? Because it's the bare G, but that bare G at 0, 0 includes everything, the entire effect of the left lead, right? So this is the left connected green function of 0, 0. And so the first term I'm going to write is simply from taking this term for G0J and substituting into here. And so I'll get exactly what we had last time, a bare G times this T, G left connected T. So that's this first term I'm writing, or the second term I'm writing here. So I've got T10 G 0, 0 left connected, T01. Sorry, the colors don't mean anything. I just forgot to switch back. G1J plus same term for the right side, GIN TN n plus 1 G right connected n plus 1 comma n plus 1 T n plus 1 comma n, and for the full G n J. And that last term, would have come out if we had done the same kind of calculation here we did for this for this guy over here. We need to write a second Dyson equation. It's in the notes, and that's where this term comes from, the last term here. But you can see it's the same form. You got one term from coupling to the left lead, one term from coupling to the right lead. So this is your coupling to the left lead, this is your coupling to the right lead. They both have that form of the self-energy T surface green function T, right? So these are the self-energies due to coupling to the left and the right lead. So due to coupling to the right lead, I'm sorry, N comma N, and this is coupling to the left lead. And so you know, these sigmas, we can do what we did before, and you define a matrix. Define a matrix sigma, which has only two non-zero terms. And the two non-zero terms are sigma 1, 1 and sigma n, just like what we did in chapter 1. And then if I do that, then this equation up above becomes Gij is equal to little g ij plus some kl little g I comma k sigma k comma l big G l comma j. Where this is a matrix, this is what I'm writing here. That should be indices, sorry, subscripts, not, those are subscripts, k comma l, or yeah, k comma l, k comma l. Right, so this matrix here is this matrix here. The matrix of two non-zero terms, 1, 1 and n, right? So this equation in green is the same equation at the top of the page. I've just defined these two terms. But you know, this is just the writing out matrix multiplication. So now if I think in terms of matrices, I simply have G is equal to little g, the matrix that goes from 1 to n, right? Plus G sigma G in matrix form. And if we multiply through on the left side with G inverse, so G inverse is equal to E minus H D, where HD is just my device part of the Hamiltonian running from 1 to n, right? Not connected to the leads. So I multiply through on the left with G inverse, and I simply have E minus H sub D minus sigma, due to coupling to the leads, acting on G, is the identity, which is the equation we've derived over and over. And the form of these self-energies are exactly what we had in chapter 2. These T surface green function T, and exactly what you're using in homework 2. So all I did was I took this whole equation and I multiplied by G inverse to get down below, and then move that sigma G term to the left-hand side. Okay? So I guess this is a good time to take a break. Do you want to ask your questions now? Or? A good time. This is a good stopping point. Then we move into the real nitty-gritty of the recursive green function algorithm.